Good morning, children. Hope you are keeping safe, healthy, fit, and fine. Today we are going to begin with chapter 8, D and F block elements. This chapter is very important for your board exam because 5-mark question you can expect from this chapter. Apart from that, many reasoning based questions can also be asked. So, let's get started. So as we know that D block elements are placed in the middle of the periodic table, right? I'll be showing you periodic table soon. And what are the groups? We know that in a periodic table there are 18 groups. And group 1 and group 2 are basically your S block. Here is your periodic table. So let me fix it for you. Yeah, here we go. So group 1 and group 2, as I said, it's S block, wherein from group 3 to group 12 is your D block in the middle of the periodic table. Whereas towards the extreme right of you, if you go, that's your P block. So right side of yours is your P block, which begins from group number 13 to group number 18. And the part of the elements from D block have been placed at the bottom of the periodic table, which is known as F block. And in this F block there are two series. The first series is basically your lanthanoids and the second series is your actinoids. This I'll be talking a little later. So what is special in these D block elements? It's their configuration. So here I'm going to highlight the configuration for you. It's N-1 D 1 to 10 NS 1 to 2. What exactly it means? N stands for the principal quantum number, which you have already learned in grade 11. So this is your general electronic configuration. In general, N-1 D1 to 10 signifies that N-N is your penultimate shell next to the first shell, right? So if you go from outside to the inside of the atom. So in N-1 shell you can have electrons from 1 to 10, and that's very special thing which all these elements have. If any one element amongst these D block elements has complete D subshell contained with 10 electrons, it is not considered as true transition element. That's a very important point. For example, if I show you this periodic table, the last elements, I mean group 12 elements, that zinc, cadmium and mercury, all these three elements have D10 configuration. They have 10 electrons in your D subshell. So since D orbital contains fixed number of 10 electrons, that is, it's the complete capacity of the D subshell to accommodate, or D orbital to accommodate 10 electrons, but yet they are not considered as true transition, although they have been placed in D block because they contain the electrons in their D subshell. So that's very important question, board question. Which elements are not considered as true transition elements? So here I am highlighting it for you. Zinc, cadmium and mercury is the answer, and reason I already told you, because they have complete D orbital, that is 10 electrons sitting there. Now another important thing is this D block basically consists of three series. What are those three series? The first series is this one, okay? That's called as 3D series. This entire series is called as 3D series. The next series is your 4D series. I'll write over here for you, 4D series. And The third one is called as 5D series. Again, I'll write it down here for you, 5D series. Likewise, there is the last one which is known as 6D series. Here I will write it for you, 6D series. So this entire D block consists of 4 series, 3D, 4D, 5D and 6D. Why do we call it as 3D series? First of all, there is an involvement of D orbital. 3 signifies what? That the number n minus 1 is 3. So what should be n for it? N should be 4 for it. So n minus 1, that's the penultimate shell, is 3. Likewise for 4D, n should be 5 and n minus 1 stands as 4. For 5D series, n stands as 6 and n minus 1 as 5. Likewise 7 here and n minus 1 as 6. So basically what I want to emphasize over here is this configuration is very, very important to understand. Okay, now we move on to the next part. So here again you can just breeze through the periodic table. Okay, one very important thing, you need to memorize the elements of the 3D series. That's scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. And all these elements are equally important for the next chapter, chapter 9. So please memorize this 3D series at least. Okay. Next very important thing is over here. One, I told you, zinc, cadmium and mercury are not considered as true transition elements. Next very important thing is copper, silver and gold. Although copper, silver and gold, they contain 9 electrons in their d orbital. But if you remember, we learnt in grade 11 to attain extra stability, one of the electron from s orbital jumps into the d orbital. For example, I'll take one example for you. Let me take an example of copper. The atomic number of copper is 29. Very important, listen carefully. How do we write the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6. Then comes what? Yeah, 4s2. And then comes 3d9. So 4s, although is the outermost shell, but it is filled before 3d. We have already learned n plus l rule in grade 11. That's because of that. Now to attain extra stability, what happens? One of the electron from s jumps into d. So its electronic configuration, instead of remaining 4s2 3d9, it becomes 4s1 3d10. Now since there are 10 electrons in d orbital, therefore copper attains extra stability. Remember this point. Likewise, very important, we learned the other element is chromium of the same series. So here is your chromium and this is your copper, what I was talking about. Now chromium, if you see, it's 24. The atomic number is 24. And its configuration is written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then what? 3d4. Again, what happens? One electron from s orbital jumps into d to attain extra stability, and therefore the configuration, instead of 4s2 3d4, it becomes what? I'll write it down here for you. it becomes 4s1 3d5. That's very, very important. Again, one electron from s orbital has jumped into d orbital to attain extra stability. So remember this exception of chromium and copper in the series. So hopefully this point is clear to you. We'll move ahead. Okay, another very important point, the FAQ, which I wanted to discuss with you. What are the characteristics of transition elements and why are they called transition elements? Which of the D block elements may not be regarded as transition elements? I think you will be able to answer this question very well. So let me just clear it for you. Characteristic, just now I told. They should have incomplete d orbital. If they don't have incomplete d orbital, they are not considered as true transition elements. And I've already discussed with you those three elements are zinc, cadmium and mercury because of their D10 configuration, 3D10 configuration. So that's the answer for this question. Okay, so we move ahead, and remember all the FAQs which I'll be discussing in my video are all board questions. So remember to understand it and learn it well. Okay, we move on to F block elements. As I said, F block elements are placed below the periodic table. You must be wondering why these F block elements were placed below the periodic table. They were placed below the periodic table because they're all radioactive elements. I said because they're all radioactive elements. Hence, they had no position in the periodic table. And let me show you one thing very interesting over here is, okay, let me set it for you. Yeah. We'll be learning, can you see this gap? If I ask you, yes. Let me just mark it for you. This is 57, lanthanum. After lanthanum, it's hafnium, 72. Oh my God. Where are the elements placed after 57? These are the atomic numbers I'm talking about. So 58 to 71. Where are these elements? These elements have been taken out of this periodic table and placed down as lanthanoids. Okay, reason being I told you they were radioactive elements, therefore they had no position in the periodic table, and that's what is seen over here. 58 is your cerium and 71 is your lutetium. So all these are lanthanoids. Likewise, actinoid 89, the series is known as actinoids. After 89 there is a gap, 90 to 103, and that's 90 is your thorium to 103. Therefore, both these series consist of radioactive elements and hence they were placed below the periodic table as F block elements. Hope I made it clear to you. Okay, going back to your F block. So the elements, as I said, constituting F block contain 4f and 5f orbital. So 4f is basically for lanthanoid series and 5f is for your actinoid series. Now in brief, we'll just put across here what I mentioned, lanthanoids as I said, and yes, very important thing to understand here, and this will be helpful also for you to learn when you are learning the elements of 3D series. As I said, you have to learn it. Can you notice one beautiful thing in 3D, 4D, 5D and 6D series? They are all set of 10 elements. I said they are all set of 10 elements. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Here we go. So these 10 elements comprise of each series. Each series consist of these 10 elements: 3D, 4D, 5D and 6D. But there is a gap in case of which series I said? 5D series and 6D series. And this gap consists of 14 elements down the way. So 14 elements down the way have been cut out from the main periodic table and placed at the bottom. See here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Yes. So both lanthanoids and actinoids is basically your series of 14 elements. That's why I have written down here 14 elements, 14 elements. And I already told you cerium to lutetium is your lanthanoid, thorium to lawrencium is your actinoids. Another important thing is actinoid is also known as second inner transition series, and lanthanoid is called as first inner transition series. The word inner signifies that they are part of the periodic table cut down from which series? Yes, 5D series and 6D series. Okay, so this is all done for you. Let us go ahead. This I have already spoken, so I'm not taking it up again. 3D, 4D, 5D series and 6D series as well. Okay, let me fix this. 6D series. Fine. And I already told you that all these series consist of how many elements? 10 elements in each series. So I have very clearly mentioned here. Okay, now let us discuss some general characteristics of the transition elements, because a lot of questions they ask from this part as well. The first one is metallic character, because we have already learned S block elements are all metallic, P block elements are non-metals as well as metalloids. Metalloids you have already learned. If you want, I can just show it to you. Yes, here we go, the periodic table. So what are the metalloids over here? I'll just highlight it for you. Let me take this color for you. So that's boron, silicon, germanium, arsenic, antimony, tellurium and polonium. By the way, polonium is not exactly your metalloid, it's more about radioactivity. So polonium is highly radioactive element. So these are the metalloids in your periodic table, right? So S block elements are core metals. P block, I said non-metallic as well as metalloids. Metalloids I've highlighted. What about D block? So D block elements are again all metals. And you know, I can figure it out for you here very clearly. Like copper, yes, silver, gold, of course, yes, iron is again the most common metal, chromium likewise, then you have zinc, okay, mercury, which is liquid at room temperature, platinum you might have heard about, right? So nickel, palladium and platinum over here. So all these elements are metallic in nature, and the most common metals I have already figured out for you. So we understand that they have highly metallic character. So since they are metallic in character, they should have high density, they should have high enthalpy of atomization, and they should have high melting and boiling point, which we'll be discussing in the follow-up lecture. Okay, so now let me also cover this melting and boiling point. Very, very interesting property. Since they are all metals, therefore, obviously they will have a high melting and boiling point. So what is the reason of this high melting and boiling point? It's the strong metallic bonding, and which involves not only n-1d electrons, but it also includes ns electrons. So both these electrons together give you a metallic character, or participate in, indeed I must say, both orbitals d orbital electrons and s orbital electrons participate in metallic bonding. So what do you think? How the metallic character should increase, decrease across the series? Across the series means I'm talking about 3D series, 4D series, 5D series, right? From left to right. Of course, the metallic character here, since we are talking about the involvement of d orbital electrons and s, therefore, as the number of d orbital electrons increase, the number of half filled I'm talking about, because in the beginning I told you true transition elements should have incomplete d orbital. So as the number of half filled d orbital increases, the metallic character increases. That means in a nutshell we can say melting and boiling point should also increase. Therefore, the melting and boiling point reaches towards the peak, should reach towards the peak height for D5, because D5 means we know that d orbital has a capacity of 10 electrons, 1 2 3 4 and 5 orbitals. So if I say D5 means it has exactly half filled d orbital and it's very much stable. Didn't I teach you just now that about chromium and copper? So chromium also attains stability because of exactly half filled d orbital. So basically the melting point should have been maximum, but it's an exception that for manganese, which has D5 configuration, it's least, and tectinium. So here you can see in the graph manganese and tectinium. They should have high melting point, but their melting point has dipped down. Okay, and the reason is stability, because exactly half filled d orbital attains a very high stability. Now thereafter what happens? After D5 the pairing starts, right? So after manganese, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So all these elements will start with their pairing procedure. Now for example, iron, okay, it's 26. That means the sixth electron sitting in d orbital I have to fill in here. Let me take a different color for you. Yes, here. So as soon as the pairing happens, there develops electronic repulsive forces. And due to these repulsive forces, melting and boiling point starts decreasing. Okay, so here you can see very clearly in the graphs. This graph, the first one is for 3D series, 4D series, and likewise 5D series. So clearly you can see that initially it was increasing, then it dipped down for these stable ones because of extra stability. Again it rises bit, and again there is a dipping down. And for copper it's very low. Platinum, it's very low. Okay, so why is it so? Again because of extra stability and pairing of the electrons in d orbital. So here we have learnt about melting point, boiling point and all those stuffs. So I'll just finish off this video till here. Next video will continue. If any questions, we'll discuss in next video. So keep watching and learn all these concepts very well.